So now we are at part 4 of this lecture now, type 2 error. So first of all, let me say it right away that the computation part is gonna be messy and difficult. So I'm not expecting you to be able to compute that, but I might test you on the concept of like drawing the curve, finding the area, and find the points or whatever. So now let's get into that. But before let's recall what is a type 2 error. What is it? You can Google it now, or you can look at the slide, or you can look at previous clips, or whatever you want to. But recall that we have 4 different scenarios, right? So we may believe that H now is true. Maybe we were wrong and that H now is false. I said an extra E. And we may decide to not reject or reject. So there are 2 scenarios for the hypothesis, and there are 2 scenarios for our decision. So now we have these 4 areas. In these 2 parts, like we are happy with the result, right? We believe it's true, and it's actually true. So nothing is wrong with that. We believe it's false, and it's actually false. Then again, we make the right decision. But there are problems with the other part. Right? When we reject the true statement, this is a type 1 error. And when we do not reject, when we still believe the false statement, that's a type 2 error. So now we have talked about how to minimize that, how to get the value, set up a policy so that we kind of adjust the type 1 error here. But now we are going to look at this sibling, the type 2 error. And this is kind of like a little bit more difficult part. So now we have this table. The reason we put the alpha that we put at the beginning, the significance level, is this part is the error that we want to minimize. Because we cannot be 100% sure, we have to have some error in our decision making. If H1 is true, if H now is true, that means we actually have this kind of nice normal curve. That means there's a chance that we will reject, that we will make an incorrect decision. And most of the times, most of the samples will fall into this nice area, this large area on the right, most of the time. But sometimes, on a rare chance, like by pure luck or any other random factors, then we are gonna get here. And once we get here, our policy tells us that we have to reject H now. In this case, we incorrectly reject the hypothesis. So that area, it's gonna be the same number we put here. If we want that case to be small, recall the example when we talk about patients. Whether he's alive or dead, and should we treat him or not. If he is alive and we reject and we don't treat him, he will be dead. That means maybe we don't want people to be dead, so we have to minimize that error. So maybe in that scenario, let's say we want that to be maybe this low, like 0.01%, and that's fine, like, because again that's the number that we set up at the beginning. It can be any number you want to, between 0 and 1, of course, because that's the chance. Right. But then that number will affect these 2 numbers. Right. The thing is, we cannot just set these 2 numbers separately. It's not like we put alpha here we can let alpha to be 0.01, and again we can let beta to be we can let that to be 0.1, 0.12. Right. Again, that is not impossible, but when you reduce the value in one entry, the value in the other entry will decrease. Right? They are what's the word for it? They are not proportion. They are in an inverse proportional. So what you can do here, you can only set the alpha, and then you can compute for the value for the other error here. And once you have alpha, then you're gonna get that with some initial conditions. So now we are gonna talk a little bit, just give you one example about how to compute that chance. Right. And we have another fancy word. This is called the power of a test. Right. Given a sample parameter x bar, in this case I'm saying it as parameter, which means it can be the average. Oh, it's a sample, so it can be the sample mean, sample proportion, or the sample standard deviation. Okay. So you giving one of these values, then we have a chance of committing type to error, and that is what we are going to define as beta. And because we have alpha, the next letter after alpha is beta. And if type 1 is alpha, then type 2 has to be beta. Like kind of like the standard notation of math and Greek letters. And that beta is the entry on the upper right entry, and that corresponds to the case when we decline to reject, when we choose to not reject a false hypothesis. That's going to be a single number beta. And then we have the power of a test. Again, that's a fancy word, but that's just simple as the lower right corner, which is 1 minus beta x0. It is the probability of a chance that we correctly reject a false hypothesis. That a false hypothesis will be detected by the test and get away. So let's look at the note here. Oh yeah, and we just simply put, maybe I should have just one. So if we call that error beta, we just call that error, if we call that error alpha, the significance level, the other error is beta. But somehow this beta is not fixed. And this is like the most confusing part of this topic. But just let's use whatever I come up with. Like this beta is not fixed. It's not like if alpha is 0.01, beta is gonna be some fixed nice number. Like no, beta is not fixed. Beta is gonna depends on the sample parameter. So anyway, you're gonna get some beta, and then that other part is gonna be 1 minus beta of x0, and these two columns adds up to 1. So we have this one, which is what we have worked before so far, and this one is the new one. What happens if the hypothesis is actually false? So we want to minimize alpha. We want that alpha to be small, which means we want that to be large. We want that to be close to, maybe close to 100 or large enough. Why? Because it is the part where we are happy with. We are happy that we are correct. And so we want that number to be large. Likewise, we want that number to be large. we want 1 minus beta to be large, because that again this the part we are happy with. We reject the false hypothesis. So the larger the better. So that's why they have to like give it a fancy name, the power of the test. The higher the value is, the higher 1 minus beta is, the more power the test has. Kind of makes sense, right? If you think about it. So just a quick comparison between these type 1 and type 2 errors. For the type 1 error, or the alpha, the first one, is the incorrect rejection of a null hypothesis. That means this is the case, the chance that we will reject the correct or the correct, the true hypothesis, and we set that number to be alpha. We analyze, we study the bell curve, and if we want that chance, that error to be alpha, then we want to get the area to be alpha, and then we can set in advance before we even collect samples. And this alpha is not affected by sample size, because if we set alpha to be 0.05, then that's 0.05 no matter how many samples we collect. The sample size might affect the distribution, but it will not affect the alpha. It's already fixed beforehand. But that will increase with the number of tests or endpoints. I'm not sure what that means, so let's remove that. So that error increase. Okay. The ratio itself is fixed. The ratio or the chance is fixed. But the total errors, the number of errors will increase. Maybe if you perform that 100 times, 5 of them will be the error. 5 times we will reject the correct hypothesis 5 times. If we increase that, we perform that 10,000 times, then we will be wrong 500 times. So that's the concept of scale. That's for the type 1 error. For type 2 is a lot more complicated. It is just a definition. It is we accept the false hypothesis. It should happen, and that's where the beta, that's where the number we put there. The probability, the number itself is beta of x0, and this beta depends on the sample size and alpha. In step 1, we choose alpha, we fix that, right? But then we can compute beta, and that will change depending on how large our sample size is. And yeah, it is explained below here that if the sample size gets larger, if you have more and more samples, then the error is gonna decrease. And in this case, I think they talk about the ratio. Oh yeah, that's again another confusing part. But the ratio is going to decrease as the sample size gets larger and larger. And likewise, we will decrease if we test more and more. Maybe if we increase from n equals to 10 to n equals to 30, instead of asking 10 students, we ask 30 students, then the beta is going to be smaller. Or if we repeat the number of tests instead of we perform 10 tests, we perform 100 traces instead, then that number is also gonna decrease. So I think it kind of like, I don't know, there's like too many ideas in here. Oh, and also it also depends on alpha. Like, as I say, we cannot just make this both of this alpha and beta to be small at the same time. If we increase alpha a little bit, then beta is gonna decrease a little bit. And then they are in inverse proportion to each other. So if you are a math person, you actually should get beta as like a function of 3 variables, n, alpha, and x0. Unlike alpha that we just put any number we want to at the beginning, beta is gonna change based on these 3 or actually like 4 or 5 variables. So that's why it's a little bit more complicated, but let's get the idea here. So what's the idea here? So let's say we have this now hypothesis and the alternative hypothesis here. So what do we do here at the start? Again, we just put this nice curve, put the mean here, and just shade the area. So we believe that the mu, the average, is at least mu0. This is what we believe. So we want to compute the beta. We want to compute the beta here. Oh, by the way, yeah, the mu0, the h now. We will follow this kind of distribution. It's a normal distribution with the center of mu0, lunar, with the spread of sigma squared over n. The variance. But now let's suppose that we are wrong. Let's suppose that we actually have alpha to be something else. Let's say mu of 1. Let's say something like here. Okay. So what we are trying to compute here, we are trying to compute the probability that we will commit the type 2 error. Okay. What happens here? We commit that with 2 conditions. We commit that when we do not reject but given that it were actually mu1. That corresponds to the top right entry. We did not reject and it was wrong in the first place. In this case, we cannot just say it's wrong. We have to say, we have to specify what should be, what we think is the actual mean. Okay, so this, and that's why I'm writing it as like beta as a function of mu0. You have to know mu0 first before you can compute beta. So we're trying to compute this part. Okay. And then let's take a look at here. Okay. If we believe that if we believe that the population mean is mu1, what it means, it means that we actually believe that the curve should look like this. We believe for the null hypothesis, we believe that the curve looks like that, but it actually looks like that. And that's these 2 different curves. So that's what it means that to believe that mu is the population mean is actually mu1. And then what it means to reject. Remember how we reject it. Okay, so maybe let's get rid of that first. When do we reject the null hypothesis? We reject that when the value is too low. And since we reject when it's too low, like we have a point here, which is what we're going to call the critical value. Right. It's called the critical value because is the value that we separate that into two areas: the area that we reject and the area that we do not reject. And by the way, that's gonna be different from the p-value. It's the same idea, but it's different. So the x bar is gonna be the point on the normal distribution on the graph. And let's say if mu is again 1000, maybe we have the critical value of 98, and that's the critical value. But nevertheless, if we move that to the p-value, right, for the p-value here, we have that cutting point alpha. Alpha here is a kind of a critical value for the p-value, and for that interval for the normal distribution. But the critical value is the value on the original graph, on the graph that we believe in the first place. And so in this case, maybe we first set alpha to be, again, let's say 0.05. We believe that alpha is 0.05, and from that value, then we can compute the critical value as a number here on the line. And that's going to be the formula here. And again, this formula is when we study about the normal standard normal distribution. This is when we juggle between the normal distribution and the standard normal distribution. And that number is going to be here. Right, it's mu naught. It's that point, right? Minus, we put minus because we believe it's on the right, right? So that's critical value. That point, the point that we put the gate on, is gonna be on the left of that. So it's minus. So to subtract by C0, or whatever it is, right? Times sigma divided by square root of n. Oh yeah. S0 is actually 0.05. That's the alpha. Yeah, that's the alpha, not the C. So anyway, so once we have mu 0 or mu naught, and we get alpha, then we find the critical point on the original distribution. So we reject when the value falls below the critical value. That means we do not reject when that value is higher than that critical value, which is this area here. So now we do not reject. Let me erase that here. Okay. That means we do not reject when the x bar, the sample, is greater than or equals to x critical. Oh, let me change the color. That means that number has to be higher than that critical value, right? Or otherwise we would have rejected that already. And then what it means that the mu is mu1. What does it mean for the population mean to be mu1? It means we have the other curve instead, right? We believe it's this curve, but it's actually that curve that is slightly to the left. That means we have that curve instead. I think yeah. So that's what it means to have a different mean, to be wrong, in other words. So now we transform from the statement about the table to mathematical statement that we can then compute, right? And so let's say how we compute that. So that's gonna take some spaces. So we have something that we believe to be true, mu0, right? And from our policy, we're gonna have the critical value, and that area, right? It's gonna be 0.05 or whatever area we put up there. So what happens is, what if we are wrong? We are wrong. We are wrong when this happened, right? We were wrong when the average is actually mu1. Which means that we have a different distribution instead. So let's so we want to find the probability or find the area under this curve that is to the right of this critical point, right? So we have the curve now, and where is the area to the right that we can see in this case? The area to the right of that point is here, this part. Right. So let's repeat again repeat one more time. What is that red area doing here? The red area is the part when we do not reject. If it's to the left of the critical point, we would have rejected already. But if it's to the right, that means we do not reject. Right. Now we want to find the part that we do not reject, and that we were wrong. We do not reject, and we are wrong. And that's why we have this curve here. And this curve here, that means we are wrong. No, the blue curve is not right. We think it should be the red one. If we were wrong, we would have the red curve, right? And to find the area to the left of that point under the red curve. Now it's the red, not the blue one. Yeah. It corresponds to this image, this part. And so from that inequality, then that's is what we have here. This one, that's the same statement, just like we just get rid of some words. And how do we compute that? Then again, that goes back to the original normal distribution. If we have x1 if we have mu1 here, and if we have x critical here, x bar critical, then that area is gonna be that probability, the area all the way to the left of that point. And actually that already suffices. Like, so you get from this image to that image on the right, they are actually the same image, but for the one on the right, I just erase the blue part because we already get the critical value, so we don't need the blue part anymore because we are wrong. The blue part is not needed anymore, right? But for that part, we can compute the area under the curve. Right. That formula suffices. But if you actually want the full formula, then again we have to transform that into the standard normal distribution. So we have, think again, how do I get it off the screen? Yeah, something like that. Now we have that, and eventually you can look at the slide that this thing is actually the test statistic, the C. Right, that's the end product. If you understand what this statement is, then you are like at 50 or 70% in the right direction. If you can do all the way through that here, that's like a cherry on the top. So from that statement, like from the word type 2 error, we transform, we change to two different statements, right? It's in that column and that row. So those two conditions have to be satisfied at the same time, and those two conditions can be transferred, can be changed into the mathematical term here, and then from that we get that image. That involves like 3 or 4 steps. So and once we have that final image, then we go back to the old school of computing the p value. Sorry, the area, the probability of something happening. Okay, that's the same image as before, just maybe better. And so this is our original assumption. And from that, and from alpha, we can set up the critical value. Oh, I'm just repeating what I said before, but in this image, we have that value here. Then, if we suppose that we are wrong, if we think that the mean, the actual population mean is here instead, then the part when we are wrong and when we accept the now hypothesis would be this yellow area. We are wrong, that means we have this curve instead. If we accept, it means the number is on the right of that critical value, and that area, that beta, is what we have, is what we want. And again, note that it depends on mu1. If you can just look at this picture. If you move alpha to be all the way to the left, if you have the blue curve here, we have the critical value here. If we move alpha to, let's say, here, then the beta is gonna be smaller than this one, because like we move the green part to the right, the area to the right is going to get smaller and smaller and smaller if we are wrong. And on the other hand, if this is what we believe, we have that critical point. But if what actually happens is here, what actually happens is that mu is greater than the value, then the area is gonna be here, which is, you can see that's large, that's close to 1, that covers almost the entire curve. So, but in this case, even if like it's large, but we don't actually have to care about that, because if the value mu of 1 is greater than the mu 0, if the value if mu 1 is greater than mu 0, that means it already agrees with our hypothesis. So we should be able to accept that without having to worry about it being false. Okay. We are not correct, yes, but like we are still, we might be less correct, but we are still correct nonetheless. So that makes sense. But if like the mu1 is greater than mu0, then we don't care about that. So that's the image. If you want a final formula, like if you say, okay, I'm okay with the idea, I just want a formula that I can compute, then here it is. You can see that it's pretty long. It's even longer than the p-value, because we we need the hypothesis, we need the alpha, and then we have to compute the critical value, that point, the green point. And after that, then we can then compute beta based on the new belief, based on that belief that the actual mu, the actual population mean is less than that value. And whatever that value it is, right? If you compute x bar crit minus x mu1, if you compute that correctly, you will get that number. Some number, let's say, I don't know, 1, and then you can plug in p of c greater than 1 into applet to give you some nice number. I think it's 0.9. I don't know. No, that can be 0.9. 0.23, I think. And whatever number it is. If you really need the final formula, here it is. Here, there, here, there. But if you just need the idea, then as long as you write the graph correctly, it doesn't have to be exact. Like as long as you know, okay, if step 1, write the graph, step 2, get the critical value. Right, for the alpha, step 3, write the new belief. Right, if we are wrong, then you should specify the new hypothesis. And then step 4, find that area. The pink area. And that area would be beta. That area is alpha. Oh, and by the way, if you understand that this image, then you can immediately see that alpha and beta are correlated. Like if you move this part like to the left here, you're gonna decrease. The alpha is going to get smaller. It's gonna lose some area, but beta now has larger area. In this case, alpha gets smaller and beta gets larger. And likewise, if you move the critical part, you change alpha, you want a larger alpha. Let's say here, right now the alpha is larger because we get a larger area. Then the area for beta now gets smaller. It was here. Okay. We used to have this the area starting from this point. But now, since we move that part, we move the critical part, the area of beta is smaller. Okay. So that agrees with our intuition on how these two areas correlated. If alpha gets larger, beta gets smaller. If alpha gets smaller, beta gets larger. And so that's why I think the concept of beta is kind of difficult to understand. So alpha is straightforward. You put the point here, right? Just that point. You want that area to be 0.5. But for beta, you have to add an additional condition of like, you think it's wrong, sure, but how wrong? What should be the new one? That's like this extra information. That kind of makes not too much sense. Oh. Anyway, let's get to the real example. Right. So now we have all the numbers here. Right. We have this hypothesis here that mu is greater than or equals to 1,000. Right. And let's suppose that we are wrong. Let's suppose that mu is actually 999. Sorry, 998. If we are wrong, then find a chance that we accept. We do not reject the wrong hypothesis. So now all these numbers are given, so we can just compute everything. Now we get the x crit. We can start with this curve like that. 1000. Sigma is 5. We want to get a point here such that this area is 0.25. Right, which we can do so by computing using the formula I provide. Sorry, it's minus. So we start from that point, right, from mu0, right? Go to the left of alpha times sigma divided by square root of n. Oh, sorry. Yeah, that was set 0. I think I say it wrong. That was set 0 or z0. So yeah. Okay, that's c0. What is c0? C0 is the part in the standard normal curve that corresponds to the point where the area to the left of that is 0.05. So that's c0 corresponds to this x critical. So we want that area to be 0.05. We can make this area to be 0.05, right? And then use this formula to change from z0 to x critical. And from that one we get mu is 1000, c0 is 1.645. So it's actually minus. And that actually like c0 is here. You just flip it. But anyway, you find a point to the left. Yeah, that's why I don't like statistic textbook, because they change. That should be plus, but that c0 is to the left, so it's minus. So let me use that. So sigma is given, right? Yes, it's 5 and square root of and it's 100. Okay. So once you finish the calculation, you get 999.18. That means this point here is 999.18. Okay. So let's suppose we just have that image. Let's not get into that for a moment. So when we have that image, that means if the sample mean is in this area, in the blue area, if we collect samples and we get an average of 999.5, let's say that's let's say x bar 1 999.5. That means it agrees with our assumption, right? In this case, we do not reject. If that number were smaller, we would have rejected this. Then it's larger. Then, if we compute the p-value, then that p-value is gonna be greater than alpha. Right? If that point x bar is to the right of that critical point, that means the area to the left, or the p-value, is greater than 0.05. And so we do not reject. So in this case, if we do not reject, right? If x bar, let's say we perform a different, we collect different samples and get x bar of 988. That means we would have reject this one. We would have reject our now hypothesis. If it were 998. In this case, we will have reject. Right. So that's just this curve. So now let's get rid of that. So now we ask the second part here is that if the curve were actually here, if the curve is not at the 1000, the center is not at the 1000, the center is at 998, then what would be the chance that we accept the wrong hypothesis? So now we are looking for, again, since we have that point already, then we can remove that. That was wrong. If that were wrong, and the actual mean here, there are too many things to. If the actual mean were 998, and we have that that point here. Let's say 99.18. Right. In this scenario, in this world, when the actual mean, the population mean is 998, we are asking for that area, because that area corresponds to the case when, in the original world, we accept the false hypothesis. Okay. So now that reduced to the problem about just finding the areas, which we can do it. Okay, so we can use the formula. Once you understand what you are doing here, then just plug in the formula, and that's the P. With the chance that the point is to the left of. Let's go back one step. Right, it's a chance that that part is greater than or equal to the critical point. Right, and then we have to add that in the different distribution now. In this distribution instead, and that is this one. We have mu1, we have x crit. We are trying to find the area to the right of this one. So what we have here, just, and if you use the formula, we transform that into the Z, into the standard normal distribution. That's crit minus mu of 1, which is the new population mean, and that gives us C greater than 2.36. And here now you can just put that into any kind of calculator, and the result is 0.0091. Okay. And yeah, that image is actually like kind of tricky, because since the standard deviation, since the mean is high, and the standard deviation is kind of small, then what we are seeing here is actually something like that. Right, and that point, that critical, is here. So that's why the area is small. It's like 0.0091, about 1 in 100, compared to the original curve here that we have erased. So what is that number? Then again you get number, but you have to be able to interpret what it means. Right? That number means there is this chance, which translates to 0.91% chance to commit types to error. And so that's the end of the line. And then we QED. We have that chance. We have a small error to commit a type 2 error. And again, we have to add like kind of an asterisk that if the average were 998 instead, Oh, that's kind of like a long, yeah, not that long, but it involves several commutations. Okay. So yeah, we have both where we have the world where we have the image of this curve of the area of the point in mind, right? And there's a word that we have to get the numbers. If you understand the image, if you have that image in mind, then you can like translate that into different kind of problems. If you have the number, then it's okay in some sense, in some case. If you have to use that number often enough, then just go with the number. Yeah, but again, I suggest you whenever you do this kind of problems, start with drawing the curves and determine exactly what each number represents, what area or what area or what value we are trying to find in this image, okay, before you go to the number side. So I think that's it for this week. Ooh. So next week we are going to do the hypothesis testing again, but now for different set of problems. See you next week.